All right, this is Vishesh, and I'm going to be presenting my Lab 1 presentation for Physics 2. So the overview of this lab was that we were creating two charged pieces of tape from a neutral piece of tape. Wanted to determine how the charged objects, the two charged tapes, would interact with other charged objects or neutral objects, and in the end we wanted to find the number of extra or lesser electrons on the charged piece of tape. Procedures involve putting a 20 centimeter piece of tape on the desk. This was a neutral desk, and this would be our base tape. Then we put another identical piece of tape over the base tape and created a U-tape. We would strip the U-tape off the base tape quickly, and this would create a charged U-tape because we're stripping electrons off the base tape. And we'd have to handle the U-tape from the ends, which is important so that we do not touch and transfer some of the electrons onto our hand from the U-tape. We repeated the last two steps to create another U-tape, and we eventually hung both U-tapes off the edge of the desk and checked interactions with a negatively charged pen, a neutrally charged object, and eventually each other. So we expected that since both U-tapes had the same charge, they would repel, and this proved to be true. And the U-tapes were also attracted to neutral objects like a book, and this is because of polarization and induced dipoles. When you bring a neutral charged object near a charged object, some of the electrons in the neutrally charged object kind of drift in one direction and cause an attraction or repel. So then we wanted to discover the charge of the U-tapes, since we knew that they were obviously charged. And if the U-tapes had a positive charge, they'd be attracted to a negatively charged pen. If the U-tapes had a negative charge, they'd repel from a negatively charged pen because like charges repel. But we found that, the U-tape were negatively charged because they repelled from the negatively charged pen. Something key to note, though, is that even if the U-tapes were neutral, they would still be attracted to the negatively charged pen because of polarization and induced dipoles, like we mentioned earlier. Then we had a question, if protons and electrons had switched charges, well, then that means that the U-tape would have been attracted to the negatively charged pen because it has extra electrons on it. So with the experiment, we had that since tape B was not moving, the net Y components had to sum to 0 when tape A was right under it. So then by the force body diagram, we have that mgb and Fa on B have to be equal in magnitude. We were given that the tape has a mass of 1 gram per meter, and we had to measure the length, which we found over here below. So then we needed to calculate what this extra charge on tape B was. So since we assume that both U-tapes have the same net charge, since they came from the same base tape, and that each tape is concentrated the charge at a single point in the center, we can sum our Y components and solve eventually for the charge on tape B, which we found to be over here, 1.78 times 10 to the negative 8th coulombs. And then using the fact that we know the charge on one electron, we can convert to the amount of additional electrons on tape B over here. Next, we wanted to find the ratio of extra electrons. So we know that the atom has approximate length of 1 angstrom, so we could find the area of one atom. And then we knew the area of the tape from length times width. So then we would convert this area of the tape to the amount of atoms that would take up the space on tape B. And after that, we wanted to find the ratio of number of electrons to number of atoms. So we divided the number of extra electrons we found earlier by the number of atoms over here. And this was 2.65 times 10 to the negative 7th electrons per atom. Some assumptions we made for this overall calculation model was that atoms are 1 by 1 angstrom units. They're all roughly the same size, and they're all tightly packed in neat rows and columns, and there's no space between them. And this allows us to calculate the rough area of the amount of space on tape B and convert it to atoms. So then if we take a look at the coding section, over here I modeled, we have tape A below, tape B above by the 2-point charges. We have F gravitational of tape B, and then we have F electric, or Fa on B over here by the green arrow. And this shows that they're equal in magnitude and that there is no net movement. If we look at the actual code over here, we can find that I've defined constants above over here that we'd be using. For the two particles, I have particle A and particle B to represent the two tapes, which are spheres. We have J hat, which is important because that's the axis that both forces are relied on, since you're going straight up or down. Then over here in this section, I'm calculating what F electric is and what F gravitational is, and note that they're both equal in magnitude but opposite in directions. After that, I found Q by using two equations. One is that F equals QE, and the other is that E equals this constant, UFPES, times Q over R squared. And if you combine those equations, you can solve for Q based on the charge of a proton, the F electric, and just that constant. And over here, I've just put in our two arrows to show the color green to be the F electric, and the F gravitational shown by the purple arrow, which you can see are both, again, equal in magnitude and opposite in direction, which shows no net movement.